Hey everybody. I want to quickly do some whiteboard work where we talk a bit about how induction works. So I'm going to focus on induction on naturals. That's the main part of the file. That's what we'll be talking about at this point. Later in the file, we'll talk about inductions on other structures, but I don't think we need a video quite for that. If I'm wrong and y'all want one, let me know in Zulip, and I'll see what I can knock together. So I want to start by writing out explicitly the principle of induction for natural numbers, and we can kind of see what it is and the way that our various metaphors, right, the staircase and the dominoes, explain how it is that induction works. What I want to stress at the outset here is that induction is not a thing that's true or false. It's a principle that people believe is a correct way of thinking about large inductive structures, right? So we think it's a good way to do proofs, and people believe it. My goal in this video is to have you believe it too, right? I'd like to explain it in a way where at the end of this explanation, you buy it. All right, let's start by saying what the principle of induction is. So the principle of induction on natural numbers n. Okay, so I'm just going to write it out for you. For all propositions P that go from nat to prop, if P of 0, and for all n prime is a natural, P of n prime implies P of S of n prime, then, for all natural numbers n, P of n. Let's take a second to comment on various parts of this. Okay, P here is a property, right? It's a function that takes a natural and produces a proposition. So what are example P's we've seen before? Well, for example, we could say something like P of n equals n equals, here I'm going to get a little, this delta here means I'm defining it. Right? There's one that we could have. Here's another one. Let's call it Q of n. Well, that could be n. Here, excuse me. Let's do something like for all m, n plus m equals m plus n. Right? That's another one that we could do. Here's another one. R of n. N equals S of n. This one's going to be, this is not a property that ever holds for any n. But like, okay, cool, whatever. These are examples of things that could go in here. One other tiny aside, maybe you haven't exactly seen this symbol before. That's just pronounced for all. And that's how we just write it out in Coq, but it's really conventional for mathematicians to use this upside down A to mean that. Right, so and now this we'll call a property of nat. Okay, so now let's see what we have. If we just look at the general structure here, if we assume thing 1 and thing 2, we conclude thing 3. Right? Now, who does that assuming? Well, okay. What the principle of induction of natural numbers says, well, if you have 1 and 2, then you can get thing 3. So the proposition here says assume this. If we assert that this is true, then we would really maybe say this better as rather than assume, we might say something like, if you have things 1 and 2, then you get thing number 3. It's kind of a question of perspective, right? We're going to have to adopt both as we go. The perspective of if you have 1 and 2, then 3 is the perspective of using induction, right? We have to prove parts 1 and 2, and then we'll get part 1 and 3. In this video, we're actually more in the assume line. We're going to say, look, suppose you had 1 and 2. Why should we believe thing 3? Okay, none of that made any reference to any of the concrete things here, so let's dig in a little deeper. P of O, what does this mean? Well, for each of these, it means something like this. So let's see what P of O would be. So here, P of O says that O equals N, excuse me, oops, not N, there's no N involved anymore, equals O plus O. Q of O, right, I'm just substituting, says that for all M, O plus M equals M plus O. R of O says O equals S of O. Let me do those little triangles again to make it clear this is not a quality, this is definition. Well, while we're explaining abbreviations, DF apostrophe DEF apostrophe N, that's a way of saying definition. Sorry. Okay. So this is basically saying, look, if you can find P of O, and then if you can find whatever this is, then we can conclude that P holds for all natural numbers N. This is the base case. Okay, next up is something pretty complicated. It's itself an implication that's quantified. There's sort of a lot going on here. Let's go through it step by step. For any natural number n prime, if P of n prime holds, then P of S of n prime holds. This, altogether, is the inductive case. Right? This is your IH, and then this will be your goal in the inductive case. If you assume that it's true for some n prime, you've got to prove that it's true for the successor of n prime. That's exactly the structure of the inductive case. Now, if you can do these things, I say, well, then go ahead and conclude that P holds for any natural number n. Let's read it once, start to finish again. The principle of induction says, for any property on naturals, if you can prove it for P of O, and you can show that P of n prime implies P of S of n prime, then you can safely conclude that P holds for all natural numbers n. Do you buy it yet? Let's take this idea and translate it to the two metaphors that we've seen. The metaphor of a tall building, of a tower with a staircase, and the metaphor of dominoes. So to do that, what I want to do is I want to name some of these hypotheses. So let's call this PB, and let's call this PI for the property rather than calling them P, let's call them H. Let's call this HB, let's call this HI. So HB is the hypothesis that, okay, somebody proved P of O. And HI is the hypothesis is, oh, somebody proved this inductive case. Now we want to conclude that for all n, that's a natural number, P of n. So let's start with the tower. So the tower looks something like this. We have a tower of numbers that looks like this. O, S of O, S of S of O. And let's say this is our number, n. Right, and this is 0, 1, 2, and so on. Now, by HB, we can find P of O directly, right? We know P of O. We just know it out of the gate. Now, how might we find P of S of O? Where are we going to find that from? Well, HI says if we know it for P of N prime, then we know it for P of S of N prime. So one layer of HI on top will get us the proof there. What about P of S of O? Well, one more layer of HI takes the proof that we had for 1 and turns it into the proof for 2. So to find P of N, you just need to build a tower n levels high, where HB, the base case, is your foundation, and HI is the staircase that gets you up level by level. You can't see it. I'm a total lunatic. I'm gesturing here in the air, and I'm not on camera. Okay, let's do dominoes. Okay, what do our dominoes look like here? Well, our first little domino, love that shape. Let's copy it. That's just O. What? Nope. All right, you know, it's going to sit a little off to the next one. And here's 1. And here's 2. And here's 3. And here's N. Okay, so we want to conclude, let me get a different color. We want to conclude P of N. So how are we going to knock that one down? Well, we can knock down 0 with HB. That's going to get us P of 0. Well, then how are we going to get P of 1? Well, we know by HI that if we can knock down N prime, if we can prove P for N prime, then we know by HI that we can also get it for P of S of N prime. So, by an application of HI, we can take the proof from PO and it knocks down and gives us the proof for P1. Okay, the same thing is true for P2. Right, we'll have another use of HI to get there. And then the same thing is true for P3. We'll have another use of HI to get there. And so on. Right? HB is the initial touch of the domino. Poke. And then HI is each domino falling over onto the next one until you hit the number that you wanted to hit. Okay, so these two are the two sort of analogical ways I have for describing how induction works. Neither of these say anything about how you use induction, right? This is all for understanding why induction is a valid principle. How do you use induction? That's a little bit different. So we're going to spend a lot of time talking about how to do informal use of induction later on, but I just want to sketch it. To use induction, to prove for all n that's a natural, P of n, there's just a couple of short steps. 1, say by induction on n. This is a performative speech act. Right? It says we're going to do a thing. 2, prove P of O. 3, assume P of n prime as your IH, inductive hypothesis. Prove P of S of n prime. And that's it. Now I want to point out, how does this correspond to the recipes I just gave before? Well, this corresponds to prove HB. And this corresponds to prove HI. And then what I want to note is that nobody here, you are not the individual who's building the tower or knocking over the dominoes. Cock is the one that's building the tower or knocking over the dominoes. What you're doing is fulfilling these proof obligations, right? Proving HB, proving HI. And then the system just believes induction, right? So the way you use it is just to prove these two hypotheses. The way you understand it is the way that these hypotheses conspire to successfully get you the facts you wanted for a number of any size. I hope this makes sense. I'm happy to talk about it. This is definitely a concept that when it's new to people, takes them a couple goes through. And I'm confident that some people in class have seen it before and some people haven't. So we're all just going to have to be patient as we sort of like get this understanding really well in everyone. I think an interesting challenge for everyone here, for people who've seen it and haven't seen it, is porting this idea to the way structural induction works. And I think once you can do that, that means you've really nailed it. That's a great test to see where you're at. I hope you're all doing well. I look forward to chatting with you about induction on Zulip, and I'll see y'all soon.